This is problem 8-60E. It's on page 449. The shape in figure P8-60 is to be made by using a metal bonding glue between the S-beam and the web of the channel. Compute the shear flow at the joint and the required shearing strength of the glue for a shearing force of 2,500 pounds. Now you've got the figure in front of you, but I'm going to jot it down or copy it down on the board because I'll need to point to it. And I'm going to copy it down in a slightly different way. Here's the C channel at the top. And since we're interested in the stress, essentially at that line, let me get another color to mark the line where we're interested in the stress. We're interested in the stress along this line, right? Since that's the case, we'll have to choose a particular area and use it to calculate Q somewhere along the way. The particular area I chose is the area beyond. Now I just realized I made a mistake because I chose all of this area. I should have this also dotted because that area is not, that means I'll have to modify my solution, okay? But that's okay. We can do that on the fly. I should get a number fairly close. Anyway, the particular area that I will choose, oh, that one doesn't work. It won't show up on board or on video or anything. Let's try this one, see what happens. Notice what I have to do is choose all the area beyond the axis of interest, okay? So, we've got a small problem here though. Well, we'll get to that in a minute. All right, so really what we're trying to do is get at the shear flow, right? And the shear flow is calculated as VQ over I. Now, what I are we talking about here? Is it the I of this beam or the I of the channel? The whole thing. The whole thing, right? That's a trick question. It's actually both together because this is all one area. Okay, so we need the I for all of this. Well, I did that. What I did is I went to the back of the book and I looked up the two shapes. This is an S12 by 50, and this is a C12 by 25. So I actually put a piece of paper back there in those two places so I could find all the properties I wanted. And I started off my solution in Excel. In fact, if you look at my solution, what you'll find is I did a lot of work in Excel just because it was easier that way. So I wrote down the part numbers, the S12 by 50 and the C12 by 25. I just read off the areas from the back. That was easy. I read off the inertia moments from the back. That was simple. Okay. Now, you have to be careful with the C channel. The C channel in the back of the book is up like this, right? But we're using it like this. So I needed the area, the area moment of inertia about this axis, which is the YY axis in the back of the book. Does that make sense? You have to be a little bit careful about that. But anyway, there it is. And what about Y? What is Y? Well, Y is the distance from the very bottom up to the centroid of the area. So how tall is that S-beam? Did you look that up yet?
12 inches.
It's 12 inches, that's right. So where's the centroid? 6 inches. Right? So that's why I've got 6 inches here in cell C2. Okay. Now we also need the centroid of the channel, and that one's not quite as easy. The way I did that is since this dimension is 12 inches, all I need is the web thickness, okay? So if you go and you look up the web thickness in the back of the book, you'll find that it is 0.387. How do I know that? Because I typed it in as a formula so that if I ever thought I made a mistake, I could go back and see what I did wrong. See, so I've got my 12 inches for the height of the S shape, and then I've got 0.387 for the thickness of the web. So that's the dimension from here all the way up to the top. So here's the extra, let's try that a little better, 0.387, okay? And then, but I want the distance from the bottom to the centroid of this shape. Okay, now be careful, I'm talking about the whole thing right now. Ignore the dotted lines for just a minute, okay? So to the centroid of that, well, where is the centroid of that shape? Well, if you look at the back of the book, you'll see that they give a distance x. That distance is 0.674, so it's 0.674 inches from this side down to the centroid of just the C channel. Okay? So, basically I took 12 inches plus 0.387 less the 0.6, whatever it was, 674. Okay? But so far, this is the simple stuff. So that gives me, not that I really needed it, but, well, no, I do need it, because I've got to find the centroid of the overall area. So there's the centroid. It's at 7.91 inches or so. Let's choose another color. So for the overall area, the centroid is a little bit above the center. So there's the centroid of the overall area, and it's 7.91 inches. The centroid. So that tells me where that's at. Now, let's see. I've also got the total area. I've got the sum of the AYs. And the main reason for that is to get that centroid. Okay, well, what did I need to do next? Well, here's where I may have made a mistake, because what I did is I included all of this area as the particular area. I wasn't thinking clearly. Really, this line here has to separate everything beyond it. So that line, and I guess I have to think about this a little more. I hadn't thought of it this way, because I don't know. We're not really interested in the stress over here. I'll show you what I did, and then we'll modify it and see what we get for our next answer, and see how much difference there is, okay? Anyway, let me explain what I did to begin, and like I said, I'm not sure that this is right. Initially, I took the particular area to be all of that area, okay? And so then, that way, it's just the area of the C channel, and so that's why I've got 7.35 square inches here for my particular area. And then Y has to be different, the distance from the centroid of the overall shape to the centroid of that area. Now the centroid of that area is just the centroid of the C channel. And so I calculated this distance as the total 12 inches plus 0.387 less basically this distance and less this distance, and that gives me Y bar. So that's what I did. If you look in the spreadsheet, you'll see that's how I got the 3.8 inches or so. So it's just 12 plus 0.387 overall height less X less Y, capital Y bar. That gives me lowercase y bar. Okay, so this distance here is lowercase y bar, whereas this distance here is uppercase y bar. Okay? So that gives me the centroid of what I was calling the particular area. Again, I'm not convinced now that that's correct. I could multiply those two together to get Q then. Okay, so AY, that is Q because that's all there is to it. There's no other portion of the particular area to consider. And so that's what I got for capital Q. Then to get the shear flow, all I have to do is plug in the shear force, which was given, what was it, 2,500 pounds? Yeah, so 2,500 pounds multiplied by the Q I found, which was, read it off for me, would you, 27 point what? Never mind, 93. And that would be cubic inches divided by the total area moment of inertia. You have to be careful here. This I is for the whole thing, okay, whereas the Q is just for the particular area. So that came out to 467.0137 inches to the fourth. So the units we end up with is pounds force per inch. From the spreadsheet, that came out to 149.5 or so pounds force per inch. And then the stress is simply Q over T, the thickness. And I took the thickness T to be just this distance here. Okay? Now we can make an argument for using this as well, but this is the section that's stressed. This is the section that it made sense to me. I'm questioning that part too, but I'll find out and get back with you for sure. So 149.5 pounds per inch. Pounds force per inch, and then T. Well, that's just the length of the web, right, or the width of the web. And if you look that up, the web width is 5.48 inches. That's the distance from here to here. It's getting a little messy. 5.48 inches, and so that's what I divided by. When I did all of that, no, why am I crossing those off? Those don't cross off, they're squared. They're multiplied by each other, so it ends up being inches squared. When I did all of that, I found that the stress in PSI is 27 PSI. It should be pretty easy to hold those two together. Now, like I said, I think I've got a mistake here because the area should be just the area beyond. Now, in a way, this area is area beyond because we can keep going out into that web. And if I'm only going to use this as the thickness, then I think this would be correct. I'll have to think about this a little farther and figure it out. What if we do it the other way? What if we say, no, the particular area is just the area beyond this axis, and then I think we can only reasonably extend the axis out here, okay? Now that would make sense. Imagine this for just a second. What if we had welded these two together? What about if somehow we had connected the C channel to the top of that I-beam permanently? It's just metal all the way through. Maybe we just formed the thing that way. Then what would we do? Well, I think then we would use an axis all the way through. So I think this is valid, okay? I think this will be the better analysis. But we'll have to be careful because we don't want the thickness T to be the entire length from here to here. We want it to be this distance plus this, because we're interested in the stress just to this side. That makes sense? We're not interested in the stress in the metal. We know the metal will be able to take it. We're interested in the stress in the glue, and that's just below the surface. Okay? So let me analyze it that way, and we'll see what happens. So that's going to, what's that? Question? Okay, well what that's going to do is that's going to change the particular area. So let's go back and figure out what would happen. What I'm going to do in my spreadsheet is just copy, let's see, is that the best way? Yeah, let's just do it this way. We'll have one alt. Okay, so now the area that I'll use will be the area just in the web of the C channel. So let's see, what would that be? I'll have to go to the back of the book and look up the properties of the C channel. Let's see, standard cross sections. I finally have put a tab in for stuff in my book like I tell you guys to do. All right, so let's go to C channels, and that is page 698, appendix A6. So reference row D is what we're looking at. That's the C12 by 25. So if we want that area, let's see, it's going to be the web thickness multiplied by the depth. So that's going to be 12 times, let's see, where's the web thickness? We've already used it, 0.387. So let's see, equals, and I'm modifying the spreadsheet if you're watching the video. 12 times 0.387. Of course, you'll just see the result, so it'll be the one alt row. Okay. Now Y, that's going to be the distance to the centroid of the particular area. If this is the particular area, well then it's just a rectangle, and the centroid is going to be half of that thickness plus this. Make sense? So Y would be equal to 12 plus 0.387 over 2. And then I can multiply those two together. Oh, wait a second. I just made a mistake. What mistake did I make? I took the distance from here to the centroid of that area. I should have taken the distance from the centroid of the overall area to there, right? So I actually have to subtract off Y bar from the number I have, capital Y bar. Almost made a mistake. So minus capital Y bar, there we go. All right, so then if we multiply the two together, we should do it. Yeah, there we go. So there's the new value of Q. What I'm going to do, I guess, is, let's see, probably the best way to do this is to just have a whole alt section. And so that's going to have the same sort of thing. It's going to have the capital Q area property. It's going to have the lowercase q shear flow as well as the shear itself. So now, let's see, now Q will be 19.88 or so. The shear flow, lowercase q, well that's just VQ over I, so it's 2500 multiplied by capital Q over, we still have to use the overall area moment of inertia. And then the stress, let's see, the stress is going to be the new shear flow, which by the way, the new shear flow number is about 106.4. So let's do it this way. for the sake of the video, tau alt is Q over T. These two are going to be different, of course, now, because we're dealing with a different area. So it's 106.4 or so pounds force per inch divided by T. And now T will have to be this distance plus this distance plus that distance. Make sense? Okay, so let's see, this will be Q divided by a quantity, and let's see, we already know that the flange here has a width of 5.48 inches, so we can type that in. But now we also need more properties of the C channel. We need to know how wide the flanges are, or how thick they are. Let's see, flange width, there it is. There's two of them. There's a TF and a BF. Which one do you think it is? I'm on page 698. It's pretty obvious if you look at the numbers. It's TF, right? It's the smaller number. It's about a ½ inch, so 0.508. Or 0.501, excuse me. So 2 times 0.501. Why did I multiply it by 2? There's two flanges. I need thickness here and thickness here added together. So I just multiplied one of them by 2. Okay. Hit enter. Now I got 16 psi. Okay. It's the same order of magnitude. So this would have to be 5.48 plus 2 times 0.501. And of course those are all inch units. And so now I've got about 16 psi. Which one's correct? I'm leaning towards this last one. I think it's probably correct. But I need to look into shear flow and see if I can actually cut it here and then continue the area on around. It seems like I'd have to do that to be consistent. But thinking of this as one solid piece, that wouldn't make any sense. So I think our second analysis is actually probably correct. Okay? Questions, comments? I don't remember who asked for this problem, but
Why did you change the thickness the second time?
why did I change the thickness the second time? I changed the thickness because the first time I just used this as the thickness, the width of the flange on the I-beam. The second time, since I was changing the particular area to just be the area literally geometrically beyond the axis of interest where I wanted the stress, since I did that, I decided I would have to use this material over here as well as part of that thickness. Remember the example, well, the problem the student asked about earlier, where there was a triangle on top with a window cut out of it? I said you had to use the thickness from both sides. Well, that would be the same principle here. Does that make more sense now?
Yeah.
Good question. Any others? Yes?
Whenever we did the example last class that was shear flow, we did use just the smaller portion.
I may have made a mistake then too.
Because
I
it
don't
was
know.
an I-beam or a 2x4.
What problem number was that? I don't recall. I've got it over here in my examples.
It was like 58 or something.
Okay. I always mark them in my book, so. 59. Okay, well in that problem, we use the thickness on either side, which would be consistent. You're talking about 59E, correct? Okay. I don't see why that's. See, the key difference here. The problem you're referring to looks like this. And let me draw it upside down if that's okay. Is that all right with everybody? Draw it upside down like this. The problem you're talking about looks like this. Okay. And what I did is I tried to solve for the stress in those areas, okay? Now, this problem is different from this one. It would be more similar if there was also some material like this, right? Then we'd have the same kind of problem. We wouldn't know if we need to also then include this thickness, okay? So I think fundamentally they're different. So I think what I did last time was okay for this one. But this would be confusing in the way this one is if it was shaped like that. Okay. But it's not.
So I thought we were using the thickness of where the two contact each other, so just.
Right, well, the thing is, again, think about this as if it was one solid mass. In fact, let's take this even farther. What if the shape was literally like this? Let's see, what if it went up? Or better yet, just went over, came down, come up, back, something like this. And let's see, that would be that surface. Well, gotta make this a little smaller. In fact, let me exaggerate so it'll be clear what I'm trying to say. See what I'm saying? What if it's all solid? Well, then if we're interested in what's going on at this cross section right here, then we have to use all of that length as the thickness. Not this, right? But these two, right? If it's solid. And so that would be kind of like it came right down there. Okay. So I think it's consistent. I think I've done the same thing in both cases. I'm either right both places or I'm wrong both places. That's what consistency is, right? Any other questions or comments on